So let's now look at the dot product of vectors. And we've seen it in 2D, and once again, the rules aren't any different in 2D and 3D. All the properties are the same. So, things we saw. If you've got two vectors, you want to find the dot product. Now, first thing, whoop, there's our formula, but that is, of course, providing that we don't have the zero vector. So if one of them has a zero vector, well, then that's not going to be true. Theta could be acute or obtuse. Now, if one of them is the zero vector, then the dot product has to be zero. There really is no other alternative on that one. If we have them as we actually know what the vectors are there, like so, to work it out, well, we multiply the x with the x, the y with the y, but now we also multiply the z with the z, and that'll get our dot product. So properties of the dot product. The maximum it could be would be the magnitude of u times the magnitude of v. In other words, cos theta is equal to 1, because that's the maximum cos theta can be, and so therefore the other end of the scale would be minus the product of the two magnitudes. U dot v is the same as v dot u. In other words, it doesn't matter what order you have them. U dot u would turn out to be x squared plus y squared, which is the magnitude of the vector squared. Dot product is not multiplication. Now, whilst the laws look very similar, we are, if you like, still expanding out the parentheses, but it's a dot product u, not a u. Right, so it's not a times u. A dot product u plus a dot product v. And so something like this is where it becomes important, because it's difference of two squares, but that difference of two squares is not the vector squared. You can't square a vector. So it's u dot u, which turns out to be the magnitude of u squared, minus, in this case, the magnitude of v squared. Now, if one of our vectors is multiplied by some scalar, which I've just labelled lambda, really it doesn't have a big effect on the dot product. You still just do the dot product u dot v, but then multiply that answer by the scalar. Now, if u dot v is equal to 0, so it was in the middle of that scale, that was quite handy, because that meant we knew that the vectors are perpendicular to each other. If it ends out at the extremities then, that means they must be parallel to each other. Now, if it turns out that it was positive, then we know those vectors are going in the same direction. If it turns out the dot product's negative, then they must be going in opposite directions. So A, B and C, three-dimensional vectors. We're going to prove that expansion product. So A dot B plus C, well, I'll put it in component form. So A is going to be A1i, A2j, A3k, and then B plus C, and I'm adding those two vectors together, I'll get B1 plus C1i and so on and so on. But now I'm going to do the dot product of those two vectors. So the i's will be multiplied together, the j's will be multiplied together, the k's will be multiplied together. Now it is algebra, so expand that all out. But if I group them in a good way, if I group the A1, B1 with the A2, B2 and the A3, B3, that would be the dot product of A and B. And the second one we're left with is A1, C1, A2, C2, A3, C3, which is the dot product of A and C. So we've proven that little property. Yeah, standard sort of question. Prove that they're perpendicular. So remember, we want to show the dot product's equal to 0. So we'll get 3 times -4, -2 times -8, and 4 times -1, and that does indeed turn out to be 0. So they are perpendicular. Here's an interesting question. Where this comes from. Yesterday, we were talking about how do you measure the slope of a line in 3 dimensions. We said, well, the slope of a line doesn't really have that much meaning. Now, what it is all to do with, it was the cosine of these angles. Right? So they're called direction cosines. If I bring it back to 2 dimensions, say, so if it was x and y, and so we've got our line, let's make it conveniently going through the origin. So that vector will make an angle with the x-axis, alpha, angle with the y-axis, beta. Now, have a look at that and think about in 2 dimensions, so we're bringing it back from 3 dimensions. What would cos squared alpha plus cos squared beta be? Well, beta clearly is going to be 90 minus alpha. So cos squared alpha plus cos squared 90 minus alpha is cos squared plus sine squared, which we know is 1. That property is true when we push it through to 3 dimensions. And so that's what we want to prove. We want to prove that indeed that property is true, that the cosine squared alpha, and that's the angle it's making with the x-axis, plus cos squared beta, the angle it's making with the y-axis, plus cos squared gamma, the angle it's making with the z-axis, is still going to be equal to 1. Okay, so u is ai plus bj plus ck. Now, if I'm trying to say what's the angle it makes with the x-axis, I could find u dot I, because the angle it's making with the vector I, the unit vector. But because that's the unit vector, then I know the dot product, A must be times 1, B would be times 0, C would be times 0, so that dot product is just A. But we also know, had we used the other formula, we would have got magnitude of u times magnitude of I cos alpha. Well, we know magnitude of u is the square root of a squared plus b squared plus c squared. Magnitude of I is, of course, 1. It's a unit vector. So we got that. Rearranging all this, that means, because they've got to be the same thing, A is equal to that expression. We end up with cos squared, if I square both sides, cos squared alpha is a squared on a squared plus b squared plus c squared. I'm not going to redo the whole thing. I'm just going to say similarly, had I done it with beta, it would have been exactly the same, but I'm now doing it with the j unit vector. I would have got b squared on a squared plus b squared plus c squared. Had I done it with the k unit vector, I would have got c squared on a squared plus b squared plus c squared. So what are those three things added together? A squared plus b squared on c squared on a squared plus b squared plus c squared, which is indeed 1. Okay, that'll do us for today.